Hello, Precalc C. Last class we learned about Descartes' Rule of Signs and via video, the upper bound and lower bound theorem. Then there were a small number of problems on the homework about this. And, you know, this is kind of nice, interesting thing to know, but it's not the most important thing in the whole world, and I don't want to spend a lot of class time going over it, so I'm just going to make a video going over this homework, and you can either not watch it at all, watch it on 2 times speed to make sure you got everything right, or you can just watch this video and just do the homework as I do it. As far as I'm concerned, it's good enough for me. Okay, it was meant to be 4 through 14 even, so let's go. Number 4 gives you a polynomial. Here it is, x cubed minus x squared plus 4x minus 6. And, well, here we go. Let's go. I want to find the big picture is I want to find the roots of this polynomial, but for now we're practicing the very specific skill, finding just simply, can I learn anything by looking at the signs of the coefficients, and I think I can, because this function is negative 6 when x is 0, but then as x gets bigger, so we're considering only positive values of x for the moment, as x gets bigger, maybe I'll just, for this one problem, I'll kind of go through the logic again. We're down here at negative 6 when x is 0, but for positive x values, 4x will contribute positively towards this polynomial. So as x gets bigger and bigger, this linear term will dominate over this constant term, so we should expect this function to go up, 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 and as it's headed towards the x-axis, it might cross the x-axis, giving us a root, but it might not. Then the quadratic term, which is destined to eventually overpower the linear term, since it has a negative coefficient, it is going to drag this function back down again. So if it's crossed the x-axis, creating a root, then this will eventually take over, creating another root. But definitely, finally, this x cubed will come to dominate for sufficiently large x. The entire polynomial and the end behavior of this polynomial is positive. And so what we might expect is this polynomial to have 3 positive real roots. Of course, it's also very possible that it starts down here at negative 6 and something different happens, like maybe the linear term brings it up, but the quadratic term brings it down, and then the cubic term brings it up. So thus I conclude, without doing any further calculations, based only on the fact that the signs go negative, positive, negative, positive, I conclude that there are going to be 3 positive real roots or 1 positive real root. Okay, I think that's pretty clear. It was pretty clear from the lesson, I think. And then the other thing to do is to consider p of negative x, which first we'll just crank it out. What does that give me? Negative x cubed minus x squared minus 4x minus 6. What is this function p of negative x? Well, it's just p, but flipped over the y-axis. So if this is now a graph of the p of negative x function, if it makes you happier to like give this function a new name or something, you know, let the cube polynomial be p of negative x, which is its own polynomial. So now applying Descartes' rule of signs to q, if I now try to perform the exact same analysis on q, I see that we start down here at negative 6. Again, I'm only considering positive x values. And this contributes negatively, this contributes negatively, and this contributes negatively. So this function is just down, down, down. It cannot have, this q function cannot have any positive real roots. Okay, but what is q, of course? It's just the reflection of p across the y-axis. And so if q has no positive real roots, then that means that p had no negative real roots. Okay, so on this first problem, I'm just going through the logic all over again. But for the rest, I'll just kind of do it really fast. And so all you are supposed to do for this whole problem, which you could do in like 20 seconds or something, is make this chart of all the possibilities. Well, as we've seen, one of the possibilities is that there are 3 positive real roots, but there are definitely no negative ones. And since it's a cubic, then there are 3 roots total, so that's all of them. But the other possibility is that there's only one positive real root, in which case, and we also saw that there were no negative real roots, so then the other 2 would be non-real. So in my opinion, the only thing I really gained from this entire last, from doing this problem, what I really gained is this. The knowledge that this polynomial has no negative real roots is a nice one, and that's kind of the whole justification for learning Descartes' Rule of Signs, I suppose, is that kind of knowledge. Okay, going faster, what is 6? 6 is a polynomial x to the 4th plus 5x squared plus 2x minus 11. And okay, if you just kind of read about Descartes' Rule of Signs, but don't actually get the sort of understanding background lesson, then you might be a little perplexed, because if you're just kind of mindlessly counting the number of sign changes, then I think even someone in one class in one of the periods asked, what happens what happens if you skip a term? So for example, this is a quartic, but there is no cubic term. The cubic term is 0. And so people are like, oh, what do we do with 0? Does that count as positive, or does that count as negative? Does that count as a sign change? I just rise above that kind of discourse and simply understand Descartes' Rule of Signs on a fundamental level. And that fundamental level is, dude, here I am down here in negative 11. Each term is contributing positively. So the 2x is going to bring me up, the 5x squared is going to bring me up even more, and the x to the 4th is going to bring me up even more. So the fact that I skipped x cubed is just completely irrelevant. Each higher powered term is going to dominate over the previous lower powered terms. That's kind of how polynomials work. And so this function is guaranteed to have exactly one positive real root. And while I am at it, I will just consider p of negative x, which is x to the 4th plus 5x squared minus 2x minus 11. And so now, by the exact same logic, it starts at negative 11, it goes down further, but then eventually 5x squared takes over, bringing it up, and it's got to cross, and this just makes it go up more. So we see that there's one sign change. The coefficients begin negative, and then they change once to positive, so that means there's guaranteed to be one negative real root. And so, in this case, by analyzing both the polynomial and the reflection of that polynomial across the y-axis, I think I've narrowed it down to only one possibility. There's guaranteed to be one positive real root. Here there's guaranteed, just double checking my work here, to be one negative real root, and thus, since it's a quartic and there are 4, by the fundamental theorem of algebra, there are 4 roots altogether, then 2 of them are non-real. Okay, so we're just kind of moving right along now. You know what, I mean, we could just practically stop. If I had just assigned 2 of these problems, that's kind of arguably enough, maybe even, because I think we get the idea. X to the 4th minus x cubed minus 11x squared plus 9x plus 8. X to the 4 minus x cubed minus 11x squared plus 9x plus 8. Yeah, okay. So what's p of negative x? Well, it's going to be x to the 4th plus x cubed minus 11x squared minus 9x plus 8. And okay, I look at the original polynomial. It starts positive, positive, but then negative, negative, but then positive again. So 2 sign changes. So that tells me that there are going to be 2 or 0 positive real roots. And then how about p of negative x? Well, that starts positive, then goes to negative, and then goes to positive. So that's 2 sign changes again, so 0 or 2. So here I learn almost nothing, right? There could be either 0 or 2 positive real roots, and there could be either 0 or 2 negative real roots. And so this is going to look like kind of like this, just to sort of truth table it out or something, those are the 4 possibilities. And so it's like 0, 2, 2, 4. It's possible that this polynomial has no real roots at all. Anyway, you can of course graph it and you can see which one of these it is, but that wasn't the purpose of this activity. Okay, 10, Foerster says in this cute little way, think about it first. He says, think. Okay, this is not that complicated. I think x to the 5th plus 4x cubed plus 2x. Okay, and I think this one, I think the best thing to do here is, hopefully this didn't confuse you that much, what makes this problem different than every problem we considered in class and on the homework is that there's no constant term, so that kind of messes with our story a little bit. But okay, let's just be serious here. What's the goal of this whole unit? It's to find roots. And if there's no constant term, then that just suggests I should factor out x. And if I do that, I get x to the 4th plus 4x squared plus 2. And if I want to know the roots of p, I just search for the roots of this quartic. And well, what can I see about this? So maybe, okay, if you want to be sort of maybe very cool about this or something, or extremely clear, then you could maybe nickname this function q. And so the roots of p are, well, 0 is a root of p for sure. And let's just find the roots of q now. But you can see that q starts out 0, or starts out positive, starts out at 2, and then this term contributes positively, and this term also contributes positively. So therefore, q, I'm not going to write this down, I'll just say it out loud, q has no positive real roots. Maybe I will just write that down. Q has no positive real roots. Okay, well, what about q of negative x? Let's check that out. Well, okay, if you plug negative x in, you just get the same thing, right? Because in fact, q is just even. So since q is just even, you know, q of negative x just is q of x. And so once again, there are no sign changes. It starts at 2, contributes positively. So when you flip q around, there's, okay, so basically q has no roots. I mean, just duh, right? This entire polynomial is greater than 0, lives above the x-axis. So therefore, what have I learned? Well, when I go to make my chart, I realize, if I didn't realize it earlier, that my chart was a little bit limiting because this same chart I've been making has neglected that there is one real number which is not positive or negative, that's 0. And so I kind of expand my chart a little bit to include a column for 0, which is relevant because p does have a 0 root. And we just learned that since q has no real roots, then p doesn't either, besides 0. And since this is a quintic, the other 4 roots must be non-real. Okay, that is all the time that's more time than we need to spend in our lives on Descartes' Rule of Signs. So hopefully you get it now. Let's do 2 more problems. Let's do 2 more problems. So once again, that was like a mess up on the homework a little bit. I intended to sign just 4 through 14 even, but I forgot the word even. I apologize if you did too many, but I'll now just do just 12 and 14 and kind of call it a day. Okay, so what is 12? So here we go, 12 and 14. What are 12 and 14? 12 and 14 are illustrating the so-called upper bound and lower bound theorems for polynomial roots. This is useful if you are sitting there by hand without a calculator, without technology, so like, not Zoom school, and you're trying to find the roots of polynomials and you're searching around for them. Okay, what is this number 12? It's x cubed plus 2x squared plus 4x minus 5. Okay, what are the directions? The directions are a little bit obscure. The directions say, find the least integer that is an upper bound for the zeros and the greatest integer that is a lower bound. This seems maybe a little bit silly, but okay, these were the directions. So let's go. What should we do? Well, let's just maybe think of this as like a real problem that we actually care about. So what are the possible rational roots? Maybe that's a good place to start. What are the possible rational roots? Well, like 1 and 5, I guess. So plus or minus 1, plus or minus 5, because the numerator needs to be a factor of the constant term, which is 5, and the denominator needs to be a factor of 1. So probably the thing to do would be to try something like 1. Alright, well, let's do that. So 1, negative 2, 4, negative 5. And, so let's go. So that's 1, so that's negative 1, 3, 3, and negative 2. Okay, so that didn't work. And not only didn't it work, but I don't even think I really learned anything at all. Okay, let's try 5 maybe, because actually, so if you're looking at this, it's negative, positive, negative, positive. So there is 1, 2, 3 sign changes. So I'm not writing this down because I don't feel like it, but now I'm at the end of the road regarding my expertise on polynomials. I know everything now. So if I'm searching for roots, I'm going to every single time, if the coefficients are rational, which they are here. Well, if the coefficients are integers, which they are, I'm going to apply the rational root theorem, which I did. I'm going to apply Descartes' rule of signs, which says that there's 1, 2, 3 sign changes. That tells me that there's guaranteed to be 1 positive real root or 3 positive real roots. So I know there's a real root somewhere, a positive one, so I'm going to look for it. So I tried 1, hoping that would be the answer, and it wasn't. I'm going to try 5 now, and well, let's see what happens. So 1, negative 2, 4, and negative 5, and we just go. So zoom zoom, 5, 3, 15, this doesn't look like it's going to work, 19, and that is, 5 times 19 is 95, so that's 90. Okay, so now, a couple things happened. The first thing that happened is, I learned that 5 is not a root. So, the only possible rational roots are 1, negative 1, 5, and negative 5. Also, I know that this function has at least 1 positive real root, if not 3, based on Descartes' rule of signs. So that means that 1 and 5 were the only possibilities. Neither of them worked, and therefore this function must have no positive rational roots. Another thing happened here, which is, and this is subtle, I talked about this in period 6 only, but I think not in periods 3 and 4, it just didn't come up. Notice something, that if you plug in 1, let's see, maybe I want to do this over here. If you plug in, one into this function, you get negative 2. Picture not to scale. If you plug in 5, you get 90. Okay, so that point is 5 comma 90, and this point here is 1 comma negative 2. Well, polynomials, being polynomials, are the most well-behaved functions in the world. And so, if my function is, they're continuous and all that kind of stuff. So if my function is negative at x equals 1, which it is, and my function is positive at x equals 5, then I know it must cross somewhere. Okay, so what I have just determined is there must be a positive real root somewhere between x equals 1 and x equals 5. And I know it's irrational, because I've tried all the positive rational roots. This is taking forever. Alright, so there's one more thing I learned about 5, and this is kind of the thing that you learned in the video. Because all of these numbers are positive, I can conclude something. And the thing I can conclude is that this polynomial has no roots above 5. And the reason is that if I have a positive remainder and an all positive coefficient quotient, then what really happened here when I tested to see if 5 was a root, I really divided by x minus 5. And I got this is my quotient and this is my remainder. So pulling the whole sort of unit together here, what this tells me is that this p function is actually just the function x minus 5 times x squared plus 3x plus 19 plus 90. And why is it helpful to write it in that format? Well, now I'm going to prove my claim I just made. The claim I just made is that if x is greater than 5, okay, well, let's finish that sentence. If you give me a number, if you plug in a number into p that's bigger than 5, if you plug 5 into a number bigger than 5 into x minus 5, of course you get something positive. What can I say about x squared if x is bigger than 5? Well, it's certainly positive. The fact that this 3 is a positive linear coefficient means that when you multiply it by a number bigger than 5, you certainly get something positive. And 19 is positive, and my remainder is positive. What I'm really saying here is that for numbers bigger than 5, if the quotient has all positive coefficients, then the entire quotient is going to be positive. And if the entire quotient is positive, but the divisor is positive as well for x bigger than 5, then the divisor times the quotient will be positive, and if the remainder is positive also, then this whole thing becomes positive. Okay, so what I just learned is that if x is greater than 5, then this polynomial p is in fact positive. And that means that it's not 0 or negative anywhere. And so p does not have any positive real roots that are greater than 5. Okay, and so the power of the upper bound theorem is I should definitely not check any more numbers bigger than 5 to see if they're roots of this polynomial, because after x equals 5, this function is positive and just getting more positive. Okay, good. So what we say is 5 is an upper bound. And that's why it's called the upper bound theorem. 5 as an upper bound is just a way of saying that the roots have to be less than 5. There are no roots bigger than 5. Okay, this problem wanted you to like push on and find the least number which is an upper bound. I think that's kind of like silly. So I sort of don't want to do it, but I don't know. I guess I'll just do it this one time. So let's do this. 1, so it's 4, so it's 2, 8, 12, 48, 43. So what does that tell you? That tells you that 43 is so because these numbers are all positive for the exact same reason. 4 is an upper bound as well. How about 3? So that means 3, 1, 3, that's 7, that's 21, that's 16. Hopefully I'm doing these right. I think I am. So that means 3 is an upper bound. This is not sort of fun. And 1, negative 2, 4, negative 5, 1. So now 2, 0, 0, 4, oh my god, 8, 3. So now 2 also is an upper bound. But finally, when I plug in 1, I see that it's negative. And so actually I can kind of update my picture a little bit, and I can say, well look, at 1, I guess this is maybe worth it, at 1 we get this point 1, negative 2, but when I plug 2 into this polynomial, I'm just double checking everything so I don't make some horrific error, but yeah, when I just plug 2 into this one, I get 8 minus 8, yep, I get 3. So that means by the time as x equals 2, I'm up here at 3. And so I've sort of narrowed it down now that actually this function is guaranteed to have a root between 1 and 2, and it's irrational. Okay, and there are no roots bigger than 2. So, to really answer this problem, you were supposed to say that 2 is the least integer which is an upper bound. Okay, this is taking forever, and we're only half done with this problem. So let's at least finish this off. I think we just won't do 14. Okay, so let's see. I think I'm going to erase everything because the other half of this theorem, which I think is a little bit more confusing, is the lower bound theorem, which applies only to negative numbers. And so let's try to search around for those. Although, in fact, okay, Descartes, well, yeah, I'm doing this in my head, but if you compute p of negative x, you get negative x cubed minus 2x squared minus 4x minus 5. And so, in fact, what can I conclude sort of immediately about this polynomial? Well, it has no negative real roots. So it is almost kind of silly to go searching for them, but suppose I do. Suppose I tried to see if, suppose I didn't notice that, and I tried to see if negative 1 is a root. Well, that becomes 1, negative 2, 4, negative 5, and now let's see what happens, checking to see if negative 1 is a root, even though I know it definitely isn't. So I get 1, negative 1, negative 3, 3, 7, negative 7, negative 12. Okay, so I kind of got what I wanted now on the sort of first try. This one is more subtle. This theorem says, and it only works in this very specific circumstance, if you are trying a negative number and the final row of the synthetic division algorithm is a bunch of numbers which are alternating in sign, so negative, positive, then you can conclude something. You can conclude that this function has no roots less than negative 1. Why? Well, once again, everything becomes totally clear if you summarize what actually happens when we did synthetic division here. And what actually happened was we checked to see if negative 1 was a root, but what that really means that we were doing is we were dividing through by x plus 1. And what did we get back? We got this quotient, which is x squared minus 3x plus 7, and then minus 12 is our remainder. Okay, and now I want to consider numbers that are less than negative 1. So if x is less than negative 1, what can I say? Well, for any number less than negative 1, x plus 1 is going to be negative. In other words, my divisor will be negative when x is less than negative 1. Alright, what can I say about my quotient? Well, here we have to be a little bit more careful. If you square a negative number, of course it's positive. What happens if x is less than negative 1? Well, it's negative. So this negative coefficient of the linear term multiplied by this negative number is going to make that linear term positive. And of course 7 is positive. And minus 12 is negative, so I'm adding a negative number. Okay, so what did I conclude from this discussion? I concluded that if x is less than negative 1 and the signs of the coefficients are as they are, then my divisor is negative, my quotient is positive, and my remainder is negative. Well, I think you see where this is going, right? If my divisor is negative and my quotient is positive and my remainder is negative, then my divisor times my quotient is negative, and therefore this is going to be negative. So what did I just learn? I just learned that if x is less than negative 1, then what I can say is that p of x is negative. And if p of x is negative and it's not, 0 or positive, it means it stays below the x-axis. So negative 1 is a lower bound, which is just a way of saying this function has no roots less than negative 1. And so to pull everything sort of back together here, what did we say? When you plug in, when you plug in 0, you get negative 5. So that's kind of interesting. When you plug in 1, I erased it, but I thought the answer was negative 2, I think it was. So that's negative 2. And when I plugged in 2, I got something like, I got 3, chop, chop, chop. And so that's 3. And then what else did I learn? When I plug in negative 1, I get negative 12. So already we're like way down here. And so I sort of have reason to believe, I'm not sure what's going on with this polynomial, but I know there are no roots. And I know that there are, I just know that there are no roots. I think this polynomial kind of looks something like that. And I know that there are no roots bigger than 2. So I conjecture that this polynomial has just one positive real root, and it's between 1 and 2, and it's irrational, and the other 2 roots are non-real. Do I have any reason to believe otherwise? I don't think so. Hopefully that's the right answer. I'm not even going to go over number 14 because this was already way too much. Good. Watch this over the weekend. And we're going to start class today with something totally different. Okay, bye.